Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture on non-reactive phase change processes. Until the last class, we have been looking at processes where there was no phase change. Today we will look at some of the fundamentals which are required for performing energy balance calculations for processes with phase change occurring. Phase change operations are very common in any chemical or biochemical industry. So you would have change in enthalpy or internal energy associated with these phase changes, which have to be accounted for when we perform energy balance calculations. Please look up the steam tables and answer this question: which has a higher specific internal energy, liquid water at 100 degrees Celsius at 1 atmosphere or water vapor at 100 degrees Celsius and 1 atmosphere? The answer is water vapor. Why? You see that numerically this is higher. But can you explain what the physical reason for this is? Molecules of a vapor can actually move around more freely compared to the liquid, hence it contributes to higher specific internal energy than the more densely packed liquids. So this is why you have a higher specific internal energy for water vapor. What could be the other explanation? During vaporization, energy is required to overcome the forces that are actually holding the molecules together in the liquid phase, so that it can actually become a vapor. So the molecules which are held together in the liquid phase is the reason the liquid is maintaining its phase. So for this phase to change from liquid to vapor, these interactions would have to be broken and energy is supplied to the molecules for this to happen. Because this energy is absorbed by the liquid molecules and they convert to the vapor phase, they have a higher internal energy, and this is the reason we have higher internal energy for vapor phases compared to liquid. When you compared the specific internal energy for liquid water and water vapor, you saw that the specific internal energy for water vapor was higher. Now calculate the numerical difference between the specific internal energy of liquid water and water vapor at 100 degrees Celsius and 1 atmosphere. Do the same thing for specific enthalpy. Which of these is higher? You would find that the specific enthalpy change between the liquid and the vapor is much higher than what you observe for the specific internal energy change. This is because the specific volume is higher for vapor, as enthalpy accounts for internal energy and the PV cap term. The value in difference is higher for specific enthalpy compared to specific internal energy. Phase changes are thus accompanied by huge changes in internal energy and enthalpy, and this has to be accounted for when we perform energy balance calculations. So it is important to understand the fundamentals associated with such processes. The difference between the internal energy or enthalpies of the liquid phase and the gas phase, or the solid phase and the liquid phase, are due to something called as latent heat. So we talked about sensible heat, which is the heat which is taken up by a system to increase the temperature. So that we have looked at earlier. So what is latent heat? Here the heat supplied does not help in increasing the temperature of the system, however it goes into changing the phase of the system. So latent heat is the specific enthalpy change associated with the transition of a substance from one phase to another at constant temperature and pressure. So this is also called as the latent heat of phase change. You have different types of latent heats. So this is different from the sensible heat. Sensible heat, as I mentioned, helps in increasing the temperature, whereas latent heat helps in changing the phase. Latent heat of vaporization is the specific enthalpy change for transition of liquid to gas at given temperature and pressure. So for water, heat of vaporization at 100 degrees Celsius and 1 atmosphere, which is also called as the standard heat of vaporization, is 40.6 kilojoules per mole. Latent heat of condensation is the specific enthalpy change of transition of gas to liquid at a given temperature and pressure. Now that I have given you the heat of vaporization for water at 100 degrees Celsius and 1 atmosphere, can you identify what would be the heat of condensation of steam at 100 degrees Celsius and 1 atmosphere? The process is the reverse of the first process, which means the heat associated, the enthalpy change associated would be the negative of the value given. So, the heat of condensation would be negative of heat of vaporization. So, the numerical value for heat of condensation of steam would be minus 40.6 kilojoules per mole when the steam is condensing at 100 degrees Celsius and 1 atmosphere. Latent heat of fusion or heat of melting is the specific enthalpy difference between the solid to the liquid forms of a species at given temperature and pressure. Heat of fusion and vaporization at 1 atmosphere is given in Perry's handbook and many other handbooks, or even in some of the textbooks prescribed. These are called as the standard heats of fusion and vaporization. These are commonly available for performing energy balance calculations. Heat of phase change is strongly dependent on temperature and it is almost independent of pressure. So, depending on the temperature at which the phase change happens, the heat of phase change would also be different. So, the values we get directly from tables are usually the standard heat of vaporization or standard heat of fusion, which means whenever we perform energy balance calculations, the phase change happens at the specific boiling point or melting point of the substance. So, that way we can directly use the value from the table, which would be the standard heat of phase change, specifically standard heat of vaporization and melting. As I was explaining, what you do is you would want to use the tabulated latent heat which is available for specific temperatures, and if the process itself is happening at a different temperature, then you would build a hypothetical path. One of the steps in the hypothetical path would have to be the phase change at the temperature for which the latent heat is available. Then you can use the data given for that particular step, and for the other steps which are the hypothetical steps in the process, you would calculate the change in enthalpy using either integral Cp dt or V cap delta P, or assuming it to be 0 and so on. So, depending on the type of process which is happening. So, here is an example problem. This is a very simple and straightforward example problem. You have been asked to calculate at what rate heat must be transferred to a liquid stream of methanol at its normal boiling point to generate 1500 grams per minute of saturated methanol vapor. So, to calculate this, we need to know the heat of vaporization at its normal boiling point. So, normal boiling point would be the boiling point when pressure is 1 atmosphere. The standard heat of vaporization for methanol at its normal boiling point is given as delta H cap V, which is the standard heat of vaporization, is equal to 35.3 kilojoules per mole. So, we have the mass flow rate for methanol. We would have to convert that into molar flow rate, and we can use this heat of vaporization to calculate the amount of heat required. So, this is an open system, which would mean the equation for heat transfer would be Q dot equals N dot delta of H cap. So, here delta H cap would be equal to delta H cap V, because the only process happening is change in phase. So, your Q dot is equal to N dot times delta H cap V. So, your N dot can be calculated from the mass flow rate using the molecular weight. So, mass flow rate is 1500 grams per minute. Molecular weight of methanol is 32 grams per mole. So, this gives you N dot. So, using this we can calculate Q dot as 1500 divided by 32 times the heat of vaporization, which is 35.3. The total value you end up with is 1654.7 kilojoules per minute. So, this is the rate at which heat needs to be transferred for vaporizing 1500 grams per minute of methanol liquid to obtain saturated methanol vapor at its normal boiling point. So, this can also be converted to kilowatts by dividing it by 60. So, the kilowatts term would be 27.6 kilowatts. Okay. So, this is a simple calculation where we performed a very simple energy balance for a process where only phase change is happening. So, this is a very simple process because phase change happens here at constant temperature and constant pressure, and this is also happening at the normal boiling point, which means the heat of vaporization was directly available, and all we needed to do was multiply this standard heat of vaporization with the molar flow rate to get the rate of heat transfer. However, usually in real scenarios problems are a little more complicated because the phase change might not be happening at its boiling point. So, then you would have to assume a hypothetical path which would make the problem a little more complicated. In the example problem we saw, we had an open system and we were able to use the standard heat of vaporization directly. You could also have closed systems where phase change might be happening. In such a scenario, you would have to use internal energy changes. So, you can actually calculate internal energy changes as delta H cap minus delta PV. If phase change involves only solids and liquids, then delta PV is usually negligible compared to delta H cap. This is because the specific volume of solids and liquids is very small, and because of this the second term becomes small. So, and you can approximate change in internal energy to be equal to the change in specific enthalpy. However, if you have vaporization or condensation as a process where you have one of the phases being a vapor or gas, then PV is usually orders of magnitude greater than PV for gas is orders of magnitude greater than the PV for liquids, in which case you have to use this value. So, for ideal gases delta PV can be approximated to RT. So, delta U cap V can be calculated as delta H cap V minus RT. This is an approximation, however, it is useful for performing calculations for phase change operations where one of the phases involved is a gas phase. So, here is a second example problem. Again it is an open system where 100 moles of liquid N-hexane is coming in per hour at 25 degrees Celsius and 7 bar and is vaporized and heated to 300 degrees Celsius at constant pressure. You are asked to estimate the rate at which heat must be supplied. In the real process, it is a constant pressure process where heating is happening from 25 degrees Celsius to 300 degrees Celsius. So, in reality the phase change would be happening at a boiling point associated with 7 bar pressure. So, if you were to look up the vapor pressure charts, the associated boiling point for N-hexane at 7 bar would be 146 degrees Celsius. However, the heat of vaporization at 146 degrees Celsius is not available for N-hexane. We do have the value for heat of vaporization of N-hexane at 1 bar and its normal boiling point. So, the normal boiling point for N-hexane is 69 degrees Celsius. So, we would have to assume a hypothetical path where the phase change happens at this normal boiling point. So, first step is to identify a hypothetical path which can be constructed to perform the calculations. So, you have the initial state which is liquid 25 degrees Celsius and 7 bar, and the final state which is vapor 300 degrees Celsius and 7 bar. As we want the phase change to happen at 1 atmosphere, let the first step of the hypothetical path be liquid at 25 degrees Celsius and 1 atmosphere where only pressure is changing, and the second step is where temperature is increased from 25 degrees Celsius to the boiling point. So, it goes to liquid 69 degrees Celsius and 1 atmosphere. So, here only temperature is changing, and the next step is where the phase is changing. So, it goes to vapor at 69 degrees Celsius and 1 atmosphere. So, from here we can heat it to vapor at 300 degrees Celsius and 1 atmosphere, and the last step of the hypothetical path is to change the pressure from 1 atmosphere to 7 atmosphere, 7 bar actually, sorry. So, this hypothetical path has 1, 2, 3, 4 and 5 steps instead of the single step which is the real path. So, each of these steps in the hypothetical path have been constructed in a way that either pressure, temperature or the phase are changing. Not more than one of these three changes in any of the steps, which means we would be able to calculate the change in specific enthalpies for each of these steps. So, the total specific enthalpy change can be calculated as delta H cap. So, for which we would have to calculate H1 cap, H2 cap, H3 cap, H4 cap and H5 cap and find the summation of this. So, let us first calculate the change in enthalpy for the first step, which is H1 cap. So, this would be equal to V cap delta P, because there is a change in pressure for a liquid phase system. So, we can calculate V cap using the density values for N hexane. V cap would be 1 by density. So, the density from the tables can be identified as 0.659, 1 divided by 0.659 is the V cap value. Now, we have to calculate V cap delta P. So, V cap delta P would be 1 divided by 0.659 times delta P, which is 1.013 minus 7 bar, and this bar needs to be converted into units which would be recognizable for cap value. V cap is in terms of liters per kilogram. So, this is liters per kilogram. So, for this conversion we can use the R value in terms of SI units and R value in terms of bar, which would be 0.008314 kilojoules per mole Kelvin divided by 0.08314 liter bar per mole Kelvin. So, mole Kelvin will get cancelled off, bar will get cancelled off. So, liters get cancelled off here and we end up with V cap delta P in terms of kilojoules per kilogram. As hexane flow rate has been given in terms of moles, it would be useful to convert this kilojoules per kilogram into kilojoules per mole. So, we can use the molecular weight and multiply the molecular weight, which is 86.17 kilograms per kilomole, which is 1000 moles. So, from here we would be able to get V cap delta P as minus 0.0783 kilojoules per mole. So, this is the first step. The second step, so second step would have to be calculated. So, for the second step there is delta T, there is no change in pressure or phase. So, this is a simple thing. So, H2 cap would be equal to integral Cp dt, where Cp would be the Cp of hexane liquid and temperature difference is from 25 degree Celsius to 69 degree Celsius. So, Cp for N hexane liquid is 0.2163 kilojoules per mole degree Celsius. So, your H2 cap would be equal to 0.2163 times 69 minus 25, which is 9.517 kilojoules per mole. So, the step 3 for the process is change in phase. So, here the phase change is happening at normal boiling point. So, we can use the heat of vaporization directly. Delta H3 cap would be equal to delta HV cap. So, H3 cap is basically equal to 28.85 kilojoules per mole, and this is a value you look up the tables. So, there are tables available for getting this value in your textbooks and also in other handbooks. Table B1 in your Felder-Rousseau textbook actually gives the change in specific enthalpy for phase change processes, which is called as the heat of vaporization and heat of melting. So, now the step 4, which is delta T, where only temperature changes and phase and pressure are a constant. H4 cap is integral Cp dt. However, here it would be the Cp of hexane vapor and temperature increases from 69 to 300 degree Celsius. So, you can get the Cp value from the tables or from some handbook. So, this would be 0.1374 plus 40.85 times 10 power minus 5 T minus 23.92 times 10 power minus 8 T squared plus 57.66 times 10 power minus 12 T cube. So, this would be in terms of kilojoules per mole degree Celsius. So, integrating this equation with the limits of 69 and 300, you would get H4 cap as 47.1 kilojoules per mole. So, the last step for the process is delta P, which is the step 5. So, this delta P is happening for gas phase. So, assuming ideal gas behavior, H5 cap would be equal to 0, because we know that change in enthalpy for constant temperature processes where only pressure changes is 0 for ideal gases. So, using that we can ignore the last term. So, our total H cap would be equal to H1 cap plus H2 cap plus H3 cap plus H4 cap plus H5 cap. So, we have the numerical values for all of them. Using that we can calculate delta H cap as minus 0.0783 plus 9.517 plus 28.85 plus 47.1, giving you delta H cap as 85.4 kilojoules per mole. So, from here we can calculate H dot, which would be equal to the Q dot. Q dot equals delta H dot equals N dot delta H cap. So, N dot has been given as 100 moles, and from there we can calculate Q dot as 100 times 85.4 kilojoules per hour. So, which is 8540 kilojoules per hour. So, in this calculation, one thing you would have seen is the first step, which is V cap delta P, the change in enthalpy due to change in pressure for a liquid, was very small compared to all other enthalpy changes. We had 4 processes where we had accounted for change in enthalpy. The last one we had assumed ideal gas behavior and calculated the change in enthalpy to be 0. So, for the first process where you had change in pressure for a liquid, we had calculated V cap delta P. The numerical value for that was minus 0.0783, and every other value you had was orders of magnitude higher than this value, indicating that how insignificant this particular step can be. So, because of this, in some cases it is okay to assume that this change in enthalpy due to change in pressure even for liquids or solids can be 0 unless the change in pressure is very large. So, with that we come to the conclusion for today's lecture. In tomorrow's lecture we will talk about how to estimate these heat of vaporizations. I just had used values which I said I picked up from tables. So, these values are experimentally measured. However, if some values are not available to you, how can you actually get that? There are some correlations which can be used. We will look at how these correlations can be used to arrive at the answers. Until then, thank you and goodbye.